Welcome to the deep dive. Today, we're jumping right into some pretty core ideas from modern physics. We're drawing from lecture notes by Salasnich and Lorenzi.
Right. The goal here is really to give you a kind of shortcut, hitting the big aha moments in statistical mechanics, relativity, and quantum physics.
These are the ideas that basically reshaped everything in the 20th century.
Exactly. So where do we start? Well, maybe with how things used to look.
Yeah, back when classical physics seemed to have all the answers.
Late 19th century, right? They were pretty confident.
Immensely confident. Especially with statistical mechanics, it felt like they'd cracked it. They figured out how to connect the big picture, like gas pressure,
To what all the tiny little particles were doing.
Precisely. People like Boltzmann, Maxwell. They showed you could get macroscopic behavior, like thermodynamics, just from the statistics of microscopic motion. Billions of tiny collisions.
And that gave us the ideal gas law. PV equals NKB 2 octal, which is super useful. But you're saying the really deep insight was about energy. Yeah, the link between kinetic energy and temperature. It's quite profound, actually.
How so?
Well, they showed that the average kinetic energy of those tiny particles, how fast they're jiggling around, is directly tied to the absolute temperature we measure. Frag 1, 2, V2, Wrangle Fierro. Frag 3, 2, KBD2.
So temperature isn't some mysterious substance.
No, it's just a measure of microscopic motion. And that Cayley-Boltzmann's constant, that's the conversion factor. It connects the microenergy world to the macro temperature world.
Okay, so classical physics, built on this kind of statistical view, was working beautifully.
For everyday speeds and sizes, yes. But then, light happened.
Ah, the speed of light problem. Experiments like Michelson-Morley showing it's always the same speed.
Always the same, no matter how fast you're moving towards the light source or away from it, which just completely breaks the old rule.
The Galilean transformations.
Right. Classical math said speeds just add up. If you run towards a ball being thrown at you, it hits you faster. But light doesn't do that.
So the math itself had to change. Einstein and Lorentz territory.
Exactly. They needed a new framework where the laws of physics, especially Maxwell's equations for light, looked the same for all observers moving at constant speeds.
And Einstein's thought experiment was key here. The light bulb.
Yeah, the Gedanken experiment. Imagine a bulb flashes. For everyone, no matter their relative motion, that expanding sphere of light has to obey the same equation. 6 pi $2 plus y2 plus z2 equals c2 t2.
But wait, how can that be true if people are moving differently relative to the bulb? Wouldn't they measure different distances and times?
Ah, that's the crux of it. They do measure different distances and times. The only way for c to be constant for everyone is if space and time aren't fixed, absolute backgrounds.
They have to stretch and shrink.
Sort of, yeah. They warp relative to each other, described by the Lorentz transformations. Space and time mix together. Your speed affects how you perceive distance and the passage of time. It's space-time now, not space and time.
Mind-bending stuff. And the most famous outcome of all this relativity.
It has to be UROEC22.
Mass-energy equivalence. The energy an object has just by existing. It's rest energy.
Exactly. And it sets a hard limit. If you plug VCNA into the relativistic equations for something moving at light speed, like a photon,
Its mass has to be zero.
it must be. The math demands it. So relativity sets the cosmic speed limit.
Okay, so we've hit the speed limit. Now let's shrink down. The quantum revolution. It started with a problem involving light again. Black body radiation.
Right. Classical physics just couldn't predict the spectrum of light given off by hot objects. It predicted infinite energy at high frequencies, the ultraviolet catastrophe. Max Planck tackled this around 1900.
And his solution was pretty radical for the time.
Extremely radical. He had to propose that energy isn't emitted smoothly, like turning up a dimmer switch. It comes in discrete chunks, or quanta.
Like steps instead of a ramp.
Exactly. The energy is quantized. Quantized where it is just a whole number, 1, 2, 3. And h is Planck's constant.
That tiny number, $6.63, it basically sets the scale for quantum effects.
It does. It tells you how fine-grained reality is at its base. But Planck thought of it more as a mathematical trick at first. It was Einstein, again, who ran with it.
With the photoelectric effect.
Yes. That really cemented the idea that light itself is made of particles, photons. The experiment is simple. Shine light on metal, electrons pop off.
Okay.
But the weird part was, it didn't matter how bright the light was. If the light's frequency, its color essentially, was below a certain threshold, nothing happened. No electrons came off.
So a dim blue light might work, but a super bright red light wouldn't.
Precisely. If light were just a wave, more brightness, more intensity should always eventually knock an electron loose. But it doesn't.
Because it's like you need one photon bullet with enough energy.
Exactly. Each photon has energy what to on iteration. If that single photon's energy isn't enough to overcome the electron's binding energy, which corresponds to $1, it doesn't matter how many photons you throw at it.
And different metals have different thresholds.
Right. Potassium needs green light, relatively low energy. Copper needs higher energy, ultraviolet light, because its electrons are held more tightly.
So Planck's energy is chunky. Einstein says light is those chunks, photons. What finally sealed the deal on light behaving like a particle?
That would probably be the Compton effect, around 1923. Arthur Compton shot X-rays, which are high-frequency light, at a block of graphite.
And he watched how they scattered off the electrons.
Yes. And he found the scattered X-rays had a longer wavelength, meaning less energy, than the incoming ones. And the change in wavelength depended perfectly on the scattering angle.
How did that prove particle behavior?
Because he could explain it perfectly by treating the X-ray as a particle, a photon, colliding with an electron like two billiard balls hitting each other. Energy and momentum were conserved in the collision.
And the math worked out.
Perfectly. He gave this equation lambda plus lambda, where lambda is the Compton wavelength, another fundamental constant related to the electron. It was undeniable proof of the photon's momentum.
Okay, light is both wave and particle. Wild. But then, things got even weirder.
Oh yeah. Enter Louis de Broglie in 1924. He thought, well, if waves like light can act like particles, maybe particles like electrons can act like waves.
He flipped the whole thing on its head.
He did. He proposed that any particle with momentum fail has an associated wavelength. Lambda equals HPOS, matter waves.
That sounds abstract. Did it connect to anything real?
Amazingly, yes. It instantly explains something that had puzzled physicists about Niels Bohr's model of the hydrogen atom.
Bohr's model worked, but he had to just sort of declare that electron orbits were quantized, right? Their angular momentum could only be specific values, $1 or $1 equals a char, and is that?
Exactly. He put it in by hand because it matched experiments, but there was no deep reason why. De Broglie provided the why.
Wow.
If the electron is a wave, then for its orbit around the nucleus to be stable, it has to fit a whole number of its wavelengths into the circumference of the orbit, like a standing wave on a guitar string.
So the wave has to connect back onto itself smoothly?
Precisely. And that mathematical condition, fitting an integer number of wavelengths lambda weighs hpb into the orbit, leads directly to Bohr's rule for quantized angular momentum. It wasn't arbitrary. It was a consequence of the electron's wave nature.
Wow. Okay, so matter has waves. How do we describe these waves mathematically? That brings us to Schrödinger.
That's the next huge leap. Erwin Schrödinger developed the fundamental equation of non-relativistic quantum mechanics, the Schrödinger equation. It describes how the wave function, psi chi, of a particle evolves in space and time.
The wave function. What is it, though? Is the particle literally smeared out like a wave?
That's the tricky part. The interpretation, which came from Max Born, is that the wave function itself isn't the physical particle. Instead, its square modulus, T2C2, tells you the probability of finding a particle at a specific position r at time 2.
So we lose certainty. We can only talk about probabilities.
In general, yes. Before a measurement, the particle might have probabilities of being in many places at once, described by its wave function. The act of measuring collapses the wave function to a specific outcome.
That wave-particle duality, was there a definitive experiment that showed it for matter like Compton did for light?
Absolutely.
Yeah.
The electron double-slit experiment. It's conceptually the same as the classic wave experiment with light, but done with electrons, one by one.
And what happens?
It's amazing. You fire single electrons towards two narrow slits. Each electron hits the detector screen behind the slits at a single well-defined point. Particle behavior.
Okay.
But if you let thousands of these individual electron hits build up over time, the pattern they form on the screen is the classic interference pattern, bright and dark stripes that you only get from waves interfering with each other.
So each individual electron somehow knows about both slits, even though it only goes through one.
It seems that way. The wave function explores all possibilities, goes through both slits, interferes with itself, and guides the probability of where the particle electron will land. Particle and wave at the same time.
This wave nature allows for some really counterintuitive things, right? Like quantum tunneling.
Oh yeah, tunneling is a classic quantum effect. Imagine rolling a ball towards a hill. If the ball doesn't have enough energy to get over the top, it rolls back down. Simple classical physics.
Makes sense.
But in quantum mechanics, if a particle with energy E hits a potential barrier, like that hill with a height $2 that's greater than e.
It should bounce back.
Classically, yes. But quantum mechanically, there's a non-zero probability, PDT, that the particle can just appear on the other side of the barrier. It tunnels through.
Even though it doesn't have the energy to go over, how?
Its wave function doesn't just stop dead at the barrier. It decays exponentially inside the classically forbidden region. But a tiny part of it makes it through to the other side. Since this wave function squared gives probability.
There's a chance it's found there. Wow. Does this happen in the real world?
All the time. It's crucial for nuclear fusion in the sun, for scanning tunneling microscopes, even for some chemical reactions. It's real. And interestingly, the probability of it happening, PTRO, often depends exponentially on something related to the classical action inside the barrier. So even this weird quantum jump retains a ghost of the classical path it couldn't take.
Okay, we've got wave-particle duality, probability, tunneling. But Schrödinger's equation wasn't the final word, was it? It didn't include relativity.
Correct. It works incredibly well for many things, but it's non-relativistic. The next step was to combine quantum mechanics with Einstein's special relativity. Paul Dirac achieved this for the electron around 1928.
Was that just a case of plugging relativity into Schrödinger's equation?
Not quite. Early attempts like the Klein-Gordon equation had problems. Dirac's approach was different, more mathematically rigorous, and his equation was incredibly successful.
What did it achieve?
Well, first, it naturally incorporated special relativity for the electron. But more importantly, it made stunning predictions that weren't put in deliberately.
Like what?
It predicted the electron must have an intrinsic angular momentum, completely independent of its motion. We call it spin, a purely quantum property.
Spin, like up or down, the basis for qubits.
Exactly, spin 12. The Dirac equation demanded it. It also mathematically required the existence of antimatter specifically, the positron, the electron's antiparticle, which was discovered a few years later. It laid the foundation for the spin statistics theorem.
Which says?
It connects spin to particle type. Particles with half-integer spin, like electrons, spin 12, are fermions and obey the Pauli exclusion principle. Particles with integer spin, like photons, spin 1, are bosons and don't. This organizes basically all of particle physics.
So Dirac gives us relativistic quantum mechanics and predicts spin. And that spin brings us right up to quantum information and computing, the qubit.
Right. The qubit is the fundamental unit. Any quantum system with two distinct states can be a qubit. An electron's spin, up-down, a photon's polarization, horizontal-vertical.
But unlike a classical bit, which is either 0 or 1.
The qubit can be 0, 1, or a superposition of both at the same time. We write it as alpha wrangle plus beta 1 wrangle, where alpha and beta are probability amplitudes. It can represent vastly more information than the classical bit. Visually, you can think of its state as any point on the surface of a sphere, the Bloch sphere.
And the real power comes when you link qubits together, entanglement.
That's where things get really interesting and weird.
Yeah.
Entanglement is when two or more qubits are linked in such a way that they share the same fate, no matter how far apart they are. Their states are inseparable.
Like Einstein's spooky action at a distance.
Kind of. If you measure the state of one entangled qubit, say you find it spin up, you instantly know the state of its entangled partner must be down, even if it's light years away.
Instantly. Does that violate relativity? Can you send messages faster than light?
No. It's subtle. While the correlation is instant, you can't use it to send information faster than light. You still need to compare measurements classically. And there's another fundamental limit. The no-cloning theorem.
Meaning?
You can't make a perfect copy of an unknown quantum state. You can measure it, which forces it into a definite state, 0 or 1, but you destroy the original superposition in the process. You can't just quantum Xerox a qubit.
Okay, so superposition and entanglement give quantum computers potential power, even with limits like no cloning. Is there a concrete example of this power?
Sure. Look at something like the Deutsch-Jozsa algorithm. It's designed to solve a specific type of problem. Determining if a function is constant, always outputs 0 or always outputs 1, or balance outputs 0 half the time and 1 half the time.
How would a classical computer solve that?
Classically, in the worst case, you might have to check more than half the possible inputs to be sure. If there are n input bits, that could take up to $2 a one plus Dorsey-Rowan evaluations. That number grows exponentially, very quickly becomes impossible for large Ds.
And the quantum approach?
The quantum algorithm, using superposition and interference, can solve it with just one evaluation of the function, regardless of n.
1, compared to potentially billions.
Exactly. It's an exponential speedup for that specific problem. That's the kind of potential driving research into building quantum computers, using things like superconducting circuits or trapped ions.
What a journey. We went from classical clockwork, hit the relativistic speed limit, then dove into the probabilistic wave-like quantum world, and ended up at the edge of quantum computation.
It really maps the huge conceptual shifts of the last century or so, from predictable trajectories to probability waves, from absolute space and time to relative space-time.
So as we wrap up this deep dive, maybe a final thought for people to chew on, connecting back to those quantum rules.
Okay, consider the structure of atoms, the periodic table. It's governed by quantum mechanics, specifically the Pauli exclusion principle, which comes from electrons being fermions with spin 12. No two electrons can share the same quantum state.
Right. That's why electrons fill up shells, giving elements their chemical properties.
Exactly. Now, if you use the simplest quantum model, ignoring interactions between electrons, you predict the electron shell should hold 2, 8, 18, 32 electrons. This sequence, 2 into 2 tessartrons, comes from the basic quantum numbers.
Okay. But does reality match that simple prediction?
Not quite. If you look at the actual structure revealed by the noble gases, helium, neon, argon, krypton, etc., the sequence of electrons in the outermost stable shells goes 2, 8, 8, 18, 18, 32.
Ah, the 8 and the 18 repeat. Why?
It's because the simple model is too simple. It ignores the complex electromagnetic interactions between the electrons in the atom. Those interactions shift the energy levels around. To get the correct sequence, you need much more sophisticated calculations like Hartree-Fock methods that try to account for electron repulsion.
So even something as fundamental as the periodic table's structure isn't perfectly explained by the most basic quantum rules alone. Interactions complicate things.
Precisely. It makes you wonder, doesn't it? What other physical laws that we currently think of as simple and fundamental might just be approximations, masking deeper complexities caused by interactions we haven't fully grasped yet? Where else might reality deviate from our neatest models?